So now that we know a little bit about heat engines, let's try applying this to some more realistic versions of engines. And to get started, we'll start with the AutoCycle, OTTO. All right, so for internal combustion engines, we want to start with the AutoCycle. It's not spelled A-U-T-O, it's spelled O-T-T-O, but it does relate very much to the AUTO AutoCycle. All right, so here's our valve system. Here's our intake valve. Here's our exhaust valve. All right, we start with the intake valve open and the exhaust valve closed. Here's our cylinder. Here's our piston, which moves, and when it moves this rod also. So piston moves down. It causes a partial vacuum in the cylinder, and a gasoline air mixture enters through the intake valve. Okay. The compression stroke, the intake valve closes, and then the piston moves up. So that compresses your air-gas mixture. Then your spark plug fires, okay? That means you have ignition, so this air-gas mixture that's now compressed explodes, all right? That power stroke means hot burn mixture expands, and it moves the piston back down, which turns the crankshaft, okay? Then your exhaust stroke, the intake valve is still closed, but the exhaust valve opens and the piston moves up. That expels the exhaust and leaves it ready for the next intake stroke, so back over here. All right, the efficiency of the AutoCycle looks like this. It's 1 minus 1 over r to the gamma minus 1. All right, and we'll talk about what that means in a little bit. So here we have how you would draw this on a PV diagram. So this first part, right, here's your intake valve open. You have this compression, all right? This is the part where you have ignition. Here's your power stroke, and here's your exhaust, okay? So ignition and exhaust. Both of those have no change in volume, all right? And you can look at it something like this. So from 1 to 2, the gasoline sprayed in here, all right? It's compressed by the piston. Then from 2 to 3, the spark plug fires. The fuel burns too quickly for the piston to move, so you don't have a change in volume, okay? From 3 to 4, you have hot, high pressure gas that's moving the piston out. And then from 4 back to 1, you have the exhaust valve open to allow temperature and pressure back to the initial values, but we don't really change the volume, all right? So here's an example we'll go through. A small single cycle AutoCycle, so a single cylinder AutoCycle engine has a PV diagram that you can see below. Point 1 begins at STP, right? So we'll call this STP, the cylinder volume of 500 centimeters cubed. During the compression stroke, the cylinder is compressed to 1/10 of its initial volume. And during the ignition process, 500 joules of heat are added to the system. So 500 joules, that's the QH right here. And we want to know what's the efficiency of this engine, okay? So we're already given QH, that's going to be 500 joules. What else do we need to know in order to get the efficiency? Well, that means we're going to have to calculate the work out. Started. We'll take a look at this in terms of, we're going to need a lot of space for this one. So let's say we have this engine, and if we're going to try to find the efficiency, we have two different kinds of transitions here. So we're going, 1, 2, 3, 4. So from 1 to 2 and 3 to 4, we have these adiabatic processes, and then on the ends we have these isochoric processes. And we're going to want to figure out efficiency, remember, we need to find QH, and we're actually given QH as 500 joules, so we just need to figure out work out. Remember, efficiency is equal to work out divided by QH. So in order to calculate the work done, we just need to figure out the area inside the curve, and that's really just going to be the work done by the process of 3 to 4, that adiabatic process, minus the work, the negative work done from 1 to 2, because remember, we have this expansion and then we have the compression. So the expansion minus the compression, that's all we're going to need. Remember, the ones on the ends, the 2 to 3 and 4 to 1, are isochoric, meaning they don't do any work. So in order to calculate the work from 1 to 2 and the work from 3 to 4, we know that the change in thermal energy is going to be equal to the work, right, for both of these. And the reason we know that is because we know that Q is equal to 0. So that means for both of these, we can use NCV delta T. That's the change in thermal energy. And that's true for all adiabatics. So work equals change in thermal energy for these because Q equals 0. So that's going back to the first law of thermodynamics. All right, so getting started calculating things, in order to calculate NCV delta T, we obviously are looking at the things that we have in this problem, and we don't have the number of moles, and we also haven't been given the temperature necessarily. So we need to figure out both N and T. We need T at all 4 points, although I'm pretty sure we're given the temperature at 1 because we're given STP. So in order to find our number of moles, we need to go back to our PV equals nRT. We can do this for point 1 since we know standard temperature and pressure, so that's easy. We plug in all of those numbers. So remember, standard pressure is 101.3, but we don't need to do that. 101 times 10 to the 3rd pascals. Our volume is given as 500 centimeters cubed, but remember, if we're going from centimeters cubed to meters cubed, there's a 10 to the negative 6 because there's a lot of cubic centimeters in a cubic meter, to the 10 to the 6 to be exact. And then we have our constant R, that's 8.31 joules per mole Kelvin, and then our standard temperature, which is 273 Kelvin. So this gives us 0.0222 moles, and we're going to start there. So now we need to figure out the temperatures. We know temperature at point 1 is going to be 273 K, that's standard temperature and pressure. And then to get T2, we're going through what we know is an adiabatic process. So from 1 to 2, this is the first time we're really dealing with these sort of changes that are adiabatic. Going through PV equals nRT and then also our adiabatic relationship, you end up with this gamma thing, and then all we really care about for gamma is if we have a monatomic, diatomic, or polyatomic gas, okay? It's really PV gamma, and so when we plug it into PV equals nRT, we end up with this -1 that has to do with just the algebra that it takes to get there. And you can go through the book, they have this derivation in there. But now we just have this ratio to get temperature 2. We know that the volume ratio for process 1 to 2 is going to be a 10 to 1. So we're going to have a 10-fold change in volume. And that's going to be a compression, so it starts at 500 centimeters cubed, goes to 50 centimeters cubed. And then remember, this is a diatomic gas, so our gamma is going to be 1.4. We end up with 1.4 minus 1 in the exponent, so it's 10 to the 0.4 times the temperature, which is 273 Kelvin, and that gives us 686 Kelvin. So now we know the temperature at point 2. We're still going to need the temperature at point 3 and point 4. At point 3, we have to look at the process that goes from 2 to 3. And this is an isochoric process. Now, because it's an isochoric process, there's a couple different ways to do this, but the easiest way is to use the fact that we know that the heat for that process is NCV delta T, where CV is specific to an isochoric process. We already know N, and CV is a constant. We know one of the T's, and we're given Q. So we're just going to kind of work backwards from there and solve for Q, since that was given as 500 joules for this process. And we're going to solve now for T3, which is going to be look like this. So Q divided by NCV plus T2, and that's just some algebra that we did, some fast, dirty algebra. So we plug in our numbers, and that's going to look like 500 joules. You have the N for number of moles. You have this constant CV, that's a constant volume process. And then we have temperature 2, which we just calculated in the previous step. So looks like we're gonna get something pretty hot. And when we plug this in, we get 1,770 kelvins. So things are getting hot. This is an explosive process. Remember, this is heat inside of an engine. So now we have T3. Now we can move on and try to find our last temperature. That's going to be T4. And we have an adiabatic process from T3 to T4. It looks a little bit different than before, but we can still use the same formula that we used for the last adiabatic process. So we go from T3 to T4, we just use this formula again. Remember, this is a combination between the relationship between P and V for an adiabatic process plus PV equals nRT. And then we solve for T4 just using this ratio, and now we can see that it's a compression, so this ratio, instead of being 10, is going to be 1/10, and gamma is still going to be 1.4 because we're still using a diatomic gas, so 1.4 minus 1, still 0.4. Now we're plugging in T3, we solve, and we get the temperature at 4, which is 705 Kelvin, so we've cooled down a little bit. And so now we have all of our temperatures, T1, T2, T3, and T4. And so now we can finally go back to calculating work, okay? So we're given the heat, and now we need to calculate the work. Recall, the way we were planning on getting work, if you go back up to the beginning, was we know that since heat is 0 from the first law of thermodynamics, we know that the change in thermal energy is equal to the difference between work and heat. You get rid of heat, and now the change in thermal energy is equal to work, okay? So remember, work is now change in thermal energy. Change in thermal energy is always NCV delta T for these closed systems. So we're just calculating NCV delta T. And remember, we only have work for our adiabatic processes because the other ones are isochoric, which have a work of 0. So we're looking up at our temperatures, and we're saying, okay, for 1 to 2, we have 686 Kelvin minus 273 Kelvin, and that means our work for the first adiabat is going to be negative 191 joules. And remember, that's because this is a compression, not an expansion. This other one, the process from 3 to 4, should be an expansion. It's still NCV delta T, but remember, the T's are 4 and 3, not 1 and 2 in this case. So we have the same thing, 0.0222 moles. And then we have CV, which is still 20.8 joules per mole Kelvin. We just use our temperatures that we calculated for 3 and 4. So that's going to be 705 minus 1770, and that's going to give us 492 joules. Now remember, this negative sign comes from the fact that when you actually look at the first law, its change in thermal energy is equal to heat minus work, so that you get a negative sign from that. So you can see there's a negative sign from that, and then a negative sign from subtracting, and that gives you a positive sign. So the total work is going to be this 492 joules minus 191 joules, that's 301 joules, and then we go to our efficiency. So 301 joules divided by the heat put into the system, which is 500 joules, and that's going to give us an efficiency of 60.2%, which is pretty high. Here's a picture of it. We're not going to go into the great details, but it's similar to the AutoCycle. We just have different, it's just some subtle difference. So like fuel ignition, meaning heating at constant pressure, is significantly different. So instead of having this part up here that's at constant volume for the AutoCycle, you have a constant pressure process for the diesel cycle. Okay.